Hello Science 30s. In this video we're going to be talking about alpha radiation. And so first of all, before we get into the meat and potatoes of it, the numbers of it, we'll look at what it actually is. And so what I have here is I have two isotopes of the same element. And what we're going to do is we're going to break these down and try and discuss a little bit about what is alpha radiation. So on the left here, we have the element beryllium. It has a mass number of 9 because there are 4 protons and 5 neutrons, and that means that it obviously has a 4 down there for the number of protons. We then have the beryllium over here, which only has 4 neutrons and 4 protons, which means it's beryllium 8. Now there's two things, there's a couple things that are happening in the nucleus that we need to know about at this point. A lot of people get really confused, and in class usually a question comes up where someone asks me, how are those protons all together? Are they not, they're all positive, why are they not just repelling each other, and why are they even together? It doesn't even make sense. And it doesn't, I mean, up to this point, maybe it doesn't. It should, I mean, you know, there is something, guys, that is an electrical force. So there's a force electrical, which is definitely trying to push all of those protons away from each other. But there is another force that is present, and that is the strong nuclear force that is happening in the nucleus there, which is keeping that nucleus together. So there's a strong nuclear force that is holding that in. And in fact, the neutrons help that. And so what we find is that beryllium 9 right here is actually very stable. This one does not break down very much at all, and it will stay in the environment for pretty much ever. Whereas beryllium 8 is not very, it's unstable, it's called. And so what that means is that the number of neutrons has changed, which means the force of that strong nuclear force has actually changed. And it's changed so much that the electrical force is overpowering it, and it will eventually break down. It will radioactively break down and actually lead to alpha radiation. So what is alpha radiation? So alpha radiation, if we go back over here and then we take a look at this from your data booklet, alpha radiation, you look at the alpha particle, it is down at the bottom here, is a helium nucleus. So there is what an alpha particle is. We will deal with the mass another time, but there's your, that's what an alpha particle is helium. And so, or we can use that Greek letter alpha as well. And so then if we go back to that beryllium, then what's going to happen? Well, what's going to happen to this beryllium as it undergoes nuclear decay is that it's actually going to be split into two things. It's going to be split into 1, 2, and then 1, 2, and then we also have another one of those right here. And so what is this split into? This is split into, and just between those, I'll put a plus sign so we know that they're not connected to each other. We have something over on this side now. And again, it's because that electrical force is overpowering that nuclear force. And those protons are going to be repelling each other, so much so that this breaks down. And the two things that we get are going to be, you see, 2 protons and 2 neutrons. 2 protons and 2 neutrons. Well, what element has 2 protons? That's going to be helium. And so if we can then say that if this is helium, what does helium look like? Well, helium is going to be look like this: He of 4 and 2, and this is going to be He4 and 2. So then your number 4 there, of course, refers to your number of nucleons. So that's 1, 2, 3, 4 total, where we get this 4 from, and then the number of protons right there, 1 and 2. Then we have over here again the 1, 2, 3, 4, and our number 4 right there, and then our 2 protons. And so when a beryllium 8 undergoes nuclear breakdown, we get 2 products from that, and that is 2 alpha particles. Now, it is if we get into an actual example from your textbook, we will see how this changes with different bigger elements. We're obviously not going to be drawing an americium 241. That's just not going to happen. I'm not drawing 241 particles. So we're going to have to do this a little bit more mathematically now in this question. So many smoke detectors contain the isotope americium 241. Alpha particles emitted during the decay of americium 241 ionize molecules in the air, allowing an electric current to flow between the two plates in the smoke detector. During a fire, smoke particles that come between those two plates interfere with the current, setting off the detector's alarm. So A is pretty easy. State the process that produces an alpha particle. That would be alpha radiation. Okay, the second is write the balanced nuclear equation describing the decay of americium that results in an alpha particle and another product. So the way we're going to do this then is we need to come up with an equation, a nuclear equation. And the nuclear equation in this case is going to be 241 and 95 and the symbol, which is Am. And this is breaking down into, they said, an alpha particle. So the alpha particle is going to be looking like that. And we are going to get some kind of unknown product here. We don't know what this product's going to be yet. So it's going to be, we're just going to call it A, Z, and X. That's going to be our notation going forward for any unknown. So now, what we do know is that the number of protons and the number of neutrons has to be conserved. So it has to be equal on either side. And so if we take a look at this then, and I'll just put a box like this, these numbers right there are connected, and these numbers right here are connected. And so the 241 has to equal 4 plus A, and the 95 has to equal 2 plus Z. And so I think we can already see what's going to happen here. We can put this mathematically if we want. So 241 is going to equal 4 plus A, and that is that's the top number, which is equal to the number of nucleons. And then the bottom number, 95, is equal to 2 plus Z. That's going to equal your number of protons. So A in this case is going to equal 241 minus 4, which is obviously equal to 237. And then Z is going to equal 95 minus 2, which is equal to 93. And we're done the hard work up to now. Now we just need to go to our data booklet, figure out which element is element number 93 right here, because that's equal to your atomic number, and that is going to be neptunium. So we know now that this is going to be neptunium, which is a 93 down here, and we also know that the mass number of that neptunium is going to be 237, and there we are. So what we had happen in this case is that we had americium 241. So americium 241 nuclear decayed into or underwent alpha radiation, and we had one alpha particle come off from that and an unknown, and we were able to figure out that unknown was going to be neptunium 237. So now to finish this question off, all we need to do is get our final balanced equation. And so in this case, I'll switch to red, why not? We are going to have 241 95 Am, which is going to decay into one alpha particle. And our other product, which is going to be neptunium 237. And there we go. There's our final answer for this nuclear equation.